Okay guys, here's a quick little overview of the lesson from today, volumes of revolution. What we're doing here is we're using integration to calculate volume, not just area. So what we're going to do is we're going to imagine that we can make an object by a function being the outside of the object, and then we're going to rotate that function around the x-axis. And when we rotate it around the x-axis, we get a three-dimensional object. Okay, so often these are like trumpet-shaped or bell-shaped or whatever, depending on what the function is. The function determines the shape of the outside shape of the object. Then what we're going to do is we're going to imagine that we're slicing this object into a bunch of little discs or coins. They're actually mini cylinders. And so what we're going to do is we're going to calculate the volume of each cylinder and add them up. The integral does this, in fact. It acts like adding up all of the cylinders. So our formula is built like this. Instead of the volume of a cylinder, pi r squared times the height, what we're going to do is we're going to make a volume formula and use the integral to add up all of the cylinders. So volume is pi r squared, where r is the function, the radius is the function. And then dx is the tiny little bit of height. Okay? I've got it drawn on here. This little height here is, we're going to call that dx. Okay? Now that's between the function and the x-axis, and then rotating it around. We can also use this to find the volume around the x-axis when we're talking about a shape that's formed between two curves. Okay? So the difference is just like with area, we're going to have the top minus the bottom. But I want you to notice that what we're doing is we're taking the volume of the top shape, the outside, and then we're subtracting the inside function, its volume, and it removes the middle. Now we can write this as two separate integrals, or we can write this as the difference inside one integrals. And this is the one that we're going to use on our formula sheet, but they're equivalent, and it's important to know that. Here we work through a problem where the outside shape was just a straight line, y equals x. And when we rotate y equals x around the x-axis, it forms just a cone. And we have the experience from Math 10 to compare with. So just over here on the side, I worked through the volume of a cone using the Math 10 approach, and we got 9 pi. And we're just going to compare that with the Math 31 approach here. So volume equals pi r squared times the height. Now r is going to be the function. We're going to square that. And the height is the dx, the change in x. And our boundaries are 0 to 3 as defined in the question. So what we're going to do is we're going to integrate, take the antiderivative of x squared, which is 1/3 x cubed, and then evaluate it over the interval 0 to 3. And we get the same result. The next example that we're looking at is between two curves. So between two curves, the curves I've got here are y equals x squared, and then the radical. And we've got it set up here so that we can use both the positive radical and the negative radical. And you can see there's the x squared, and there's the two pieces of the radical, the positive piece and the negative piece. And the boundaries are formed by the intersection between the two. And so we get this kind of torpedo shape, or I don't know what else to call it, a pickle, pointy pickle shape. The intersections can be found by making the two curves equal to each other and then solving, and we've got boundaries at 0 and 1. So we're going to integrate from 0 to 1, and we have, here's our volume formula. This is the top radius, the bottom radius, the top function, and the bottom function, and we're integrating from 0 to 1. Pi r squared times the height, and this difference formula takes care of both. So the antiderivative of this is easier to work through after you've squared it. So square root squared, x squared squared, and then the antiderivatives evaluated over the boundaries, and we get this nice, neat, exact result, 3 pi over 10. Okay, so I'm going to invite you to work through some of these. Page 531, 1 and 2 in our textbook are great practice, and the answer keys are really clear. So good luck with that. Thanks.